We do not keep Is it okay? Okay, since it is filming, I have to address the future generations, I suppose. And they are looking from their internet living cocoons. They probably think that this is a very simplistic environment, but I have to say it's fantastic. It's a very good meeting. And if my grandchildren are watching, I'm having a lot of fun. It's a fantastic meeting. And the hospitality of George is incredible. I told him already, I want to say it in public. It's the second best in the world. Yeah, and the best in the world is his wife. Who can live with a wild bunch of impersonators of Professor Zonnebloem, or Tournesol as he's called. So I think this is not easy to have your private life invaded by a bunch of physicists and mathematicians.
On the contrary, it makes it
less private, but more active, I'm sure. Yeah. Okay, so thank you. I intend to talk about it. I call it a takeaway talk. I talk about dequantization, and in the end, there is perhaps something remaining that could be a model, which I call spaced time. So, with a D. That's nice. That's a wordplay. So I'm coming. Oh, sorry. Yes, I have to introduce myself. I'm Fred Askloster. I'm in Antwerp. I started. Well, you know, I studied in a Catholic secondary school, in a socialistic state university for a bachelor, in an anti-Catholic Free University of Brussels, which is based on Freemasons principles, for the master. I did my PhD in a Protestant university, the Free University of Amsterdam, and I did my habilitation in a pluralistic university that was at that moment just created at Antwerp. So this didn't make me any wiser, I guess, when you do that in Belgium and Holland, but it made me a tolerant person, which was perhaps good too. Then I started to work on the Brouwer group, and in fact in my PhD already I created the very first, I think, applications of non-commutative Riemann surfaces by doing non-commutative evaluation theory and extension of that to pseudo-evaluations of non-commutative algebras. In fact, I could, if I ever get there, make a relation to these pseudo places in the observables on some Hilbert space, the projective case. And there is a relation with that in my talk, in fact, at the end. But then I got into the Brouwer group, but I went to Cambridge for analytical number theory, working with Swinnerton and Dyer in 72, 73. And so I mixed a lot of number theoretical inspiration in later theories of maximal orders over number rings and so on. And I profited a lot from the German school, from Doring, Schmidt, van der Waalen, and especially Witt also, who had already a lot of non-commutative algebra that was forgotten in Europe at that time, and that was not right. And also Maas, Selbrecht, Treeswonges, Eichler. So there was really, in Antwerp, a mixing of traditions going on, I think. For example, I had with some student, Jan van Geel, we proved the Riemann-Roch theorem for algebras, non-commutative algebras over commutative curves. And this is a continuation of work that Witt already started, but we found out later via the book of van der Waalen. So this non-commutative geometry resulted in the first book on non-commutative geometry, which was a spring election of Alain Verscholen, called, what was it called? Non-commutative algebraic geometry. The PI case, it was the case of rings that were finite dimensional over their center, let's say, roughly speaking. And that was popular at that time for Borghesi's book of rings with polynomial identity. Since I wanted to make a projective space, I had to deal with graded rings, and a lot of work resulted from these graded rings in the Brouwer group of graded rings, which was applied to the Brouwer group of projective varieties, so a mixing of geometrical techniques and algebraic. And well, this went for a long time. I did a lot of work in filtered and graded rings and applications to rings of differential operators and so on. But recently, by some strange Deus ex machina, some of my work seems to be related with physics. So the things that appeared recently in Journal of Mudfish and Co-Mudfish, a few papers, some dealing with Koch and Specker, which comes because I had contact with Chris Isham a few years ago, and there is also a relation with valuation theory and line configurations in space. And some other things related to twistings, general twistings of algebras, where, for example, you can get a proof that Kahn's algebras, quantum planes or spherical manifolds, are products of commutative planes, but twisted products. So more and more of this algebra seems to be related to physics, which gives me an excuse to say this, and then to say that there's no physics in my talk. So okay, why is it a takeaway talk? Because I want to explain something about non-commutative geometry, perhaps, and then I thought, okay, let me take away all the algebra. The people don't want to see all the abstract algebra. That's where I came from, of course. Then I thought, well, let me also take away all the algebraic geometry. We don't want to do commutative or whatever algebraic geometry. It's category theory, but then I thought, well, maybe they know enough category theory. Let me take away all the category theory. Okay, the representation theory is also not really necessary. So I took away the representation theory. And then I'm left with one idea. I hope. I'm not so sure even. So it's a very, very stripped down theory that remains, which you could call something like non-commutative topology. And I only will use for that, I only use the definition of non-commutative topology, but it's basically a case of ordered, partial order, and operations that are generalization of the intersection in the union. But then I will have a problem to do shift theory at a certain point and relate it to points. And for that I made a dynamical theory in order to solve that. If you wanted to hear the mathematical version, I only wanted to sheafify, to make sheafification of a pre-sheaf, and that replaces the function theory to some extent, and to a good extent. So the mathematical reason I began to do that was sheafification. But then in the end I end up with something that may be a model. And I'll just leave it to you to decide whether there's any physics or useful for physics or not. I cannot avoid sometimes, I cannot resist the temptation of using physical words. So for a certain parameter, I will say time. I don't know whether that is time or not, but this is also up to you. So let me first, so if I do have 2 lectures, but I hear that there was a lecture missing. If it helps, then I can sacrifice my second lecture. But let's see where we get.
See where we go, Freddie.
Yeah.
See how we go, yeah.
Yeah, okay. Yeah. So, trying to make it real. That's a protest song from I talked to several people about situations in the late 60s and when I was a student. In 68 I was 21 and in the middle of the revolution. And I still have traces of that. Trying to make it real was a very good protest song compared to What is the title, but that's I inversed it. But in this sense, trying to make it real has a mathematical meaning because you try to use real numbers, and I'm against that. So I think you only try to make the real numbers real. They shouldn't be in physics. But let me start. So
sorry, what aspect of the real numbers do you not like?
The reality of it. I mean,
The reality.
I think they're not so real as they're trying to make it. No, there are too many.
Okay.
I will come to that in some point. You can use the real numbers. I'm not really against that, but I don't see the reason at the level of foundational theory. So you have a geometric or whatever object, and usually here's already a problem. You embed it in some space. Yeah, I know you can make it more abstract and glue things together, but let's say you have an embedding of an object. So immediately from that you have coordinate functions. Because on these things you have coordinate functions, you can restrict them. Right? And you can make polynomial expressions in coordinate functions, so you always have a polynomial function ring in that case, to a certain field, which I wrote K because you can choose that if you like. But now suppose that this object that you start from